So, thank you everybody for being here at the seminars of the Physics Department of Universidad Santiago de Chile. We are pleased today to have with us Professor Stacy McGaugh from Case Western University. Professor McGaugh is a chair of the Department of Astronomy, director of the Warner and Swayze Observatory of Case Western Reserve University. His primary interest is in low surface brightness galaxies, but also he studied cosmology and the mass discrepancy problem. He has worked extensively on galaxy dynamics, showing that the Tully-Fisher relation is fundamentally a relation between the rotation speed of a spiral galaxy and its baryonic mass. He successfully predicted the velocity dispersion of many of the dwarf satellite galaxies of Andromeda as they were discovered. And his contribution to cosmology include the quantitative accurate prediction of the amplitude ratio of the first to second peak of the acoustic power spectrum of the CMB. Today, he will talk about the missing mass and modified dynamics. He's an expert in the MOND, modified Newton dynamics scheme. So thank you very much, Professor McGaugh, for accepting the invitation. We're very happy to have you with us. So, yes. So
should I
you
share?
are now a co-host.
Okay.
And you can share your screen as you want.
All right, let's try it out here. Let me know if anything goes wrong. Okay, I see it. Do you see it? Okay. Well, again, thank you for having me. I apologize to speak in English, but no tengo las palabras to say all this in Espanol. I became interested in the modified dynamics in a really accidental way. I won't tell too much of that story, but I certainly didn't set out to have anything to do with it. But I hope the reasons for that become clear as we go along. I have many collaborators over the years, many of whom are listed at left, including my most recent graduate student, Ting-Fei Li, who just moved to Germany to take up a Humboldt Fellowship there. So I should change that already. Now, I'd like to talk about this in a sort of philosophical context. So it took me a long time to track down the proper attribution to this, but it seems to be to Josh Billings, and even then it's not exactly what he said, but the spirit is that what gets us into trouble is not what we don't know, it's what we know for sure that just ain't so. And an obvious example of that these days is vaccine denialism, but this can be true for us scientists as well. So a few things that we know for sure is that F equals ma, Newton's second law, of course the Poisson equation relating the gravitational potential to the distribution of mass, and what that means basically is v squared goes as gm over r. Should scale as the mass divided by the radius to give you the velocity. And from those simple considerations, it's now obvious the universe is filled with non-baryonic cold dark matter. Okay, right, that's a bit of a leap ahead. So how did we get there? This is what I call the dark matter tree. It's a sketch I made in the mid-90s to try to think about the possibilities with the important roots of the problem, the empirical evidence that led us to invent dark matter. And then the hypothesized solutions at top, all the different things that people have suggested, at least up until that time, as to what the answer could be. And I've made a modification right away because the language gets us into trouble. By calling this the dark matter problem, we immediately bias ourselves to think of it in those terms. And as Jacob Bekenstein pointed out long ago, what we really have evidence for are acceleration discrepancies, that when we apply the Poisson equation to the observed mass distribution of mass, it underpredicts the observed accelerations. And it's from that that we infer the need for dark matter. And so, of course, a famous example that I'll talk about a lot is the rotation curves of spiral galaxies tend to remain flat when they should be falling down in a Keplerian fashion. The clusters of galaxies, which are remarkable for showing the discrepancy in at least three distinct ways. One, the velocity dispersion is very high. You see this prominent gravitational lensing, which is especially obvious in this particular case. It's actually rather rare that you see it that strongly, but it happens. And of course, the space between the galaxies and rich clusters is not entirely empty. There is a diffuse intracluster medium that is very hot and can only be held in if the gravity is much greater than what meets the eye. Between Zwicky's contributions and Ort's all the way back in the 30s to Rubin's and Gosma's in the 70s and 80s, this has now established a clear need for something extra. There is new physics here, whether it be some new form of mass or a modification of one of the laws of dynamics as contemplated along this branch of the tree. It's also an important part of the paradigm that we need to form the large-scale structure of the universe. So this is a map of the entire sky where every point is an entire galaxy, which is just a mind-boggling thing to think about. And the eye can see all sorts of structure here, the long filaments and walls with mostly empty voids, and there's veining, big clusters, and so forth. And it's basically a trivial calculation to show that that can only grow to where we are now by a factor of 1,000. In conventional dynamics, and we need a factor of 100,000 to get here from the initial C and B. Of course, as an observer, we would like to hack off some of these limbs. The theorists are always growing new ideas, and like a good gardener, we have to beat it back. And at this point, we can at least rule out a lot of individual candidates and many generic classes of things. So of course, one of the first things you think is just, okay, geez, it could be very faint stars, brown dwarfs, just ordinary matter that's hard to see. Long story short, we've looked hard enough at this point, we should have seen them if there were enough of them, and they're simply not. There are some tiny parameters of corners of parameter space you might hide in, but that's really what it is. It doesn't seem like a fruitful approach to follow anymore. Then, of course, there are neutrinos, very strange story, neutrinos, because when I first heard it suggested by Hans Bethe in the 1980s that neutrinos could be the dark matter, I had just learned then as a student that neutrinos should not have mass. And so, no way. And two, okay, if they have mass, then that must be the answer, right? And of course, now we know from atmospheric and solar oscillations that neutrinos do have mass, but it's nowhere near enough to make up the dark matter. So while that is an important component of the universe, it is not the component that we're talking about, or what we mean usually when we say dark matter. What we usually mean when we say dark matter is specifically cold dark matter, and often specifically a weakly interacting massive particle. And so the two chief motivations for that are the ones I just outlined, the growth of structure and Big Bang nucleosynthesis. So this is the mass density in baryons only, normal matter, from all the different isotopes, light isotopes, over the years. And this was already a very well-established field by the early 90s. So these first few points are reviews, compilations from back then of people saying, yes, yes, we know this. You know, there are details that vary, of course, but very consistently, this number has been around 4 or 5% of the critical density, nowhere near where we had hoped to get. Of course, the total mass density doesn't add up to that either, as we had once hoped, but it's clearly bigger than the baryon density. So there's something out there gravitating that's not normal matter. We need something new that's not in the standard model of particle physics. And then there's the need to grow structure. We now observe structure in the microwave background, but it's incredibly subtle. The real story of this map, which is essentially a baby picture of the universe when it's just a few 100,000 years old, is that the universe at that time was incredibly smooth and homogeneous. The ripples there are only 1 part in 100,000. The growth rate is only about the same as the expansion rate of the universe, so these could only grow by a factor of 1,000, and yet we need them to grow by a factor of 100,000. The way to do that is to have some extra mass that can already start clumping up at these early times, which it can only do if it does not interact with the photons. So not only do we need a new particle, we need one that does not interact with photons. And it took me a long time to realize that those really strong statements are true, but only if we assume that gravity is normal. And so what seemed to me, and I know still does to a lot of people, to be an absolute requirement for non-baryonic dark matter really rests on this very obvious assumption that seems incredibly reasonable, but maybe not. So we have spent the last few decades with a most favored candidate, the weakly interacting massive particle. And this has been so strong that we've really acted like this is the answer for sure. We may have gotten less sure about it lately, but you know, every 5 years for the past going on 30 years now, I've heard some impressive person say, in 5 years, we will know what the dark matter is. Well, 30 years later, we don't. And in retrospect, it's very obvious that the speaker already knew what the dark matter was. They were sure it was a WIMP. That was the strength of conviction that we had coming out of the 80s with supersymmetry and so forth. Unfortunately, that has not worked out. The original argument in favor for WIMPs, the so-called WIMP miracle, which I will not review, argued that the cross-section should be around 10 to the minus 39. You notice that scale does not even appear in the plots you can generate with the dark matter tools at Brown. By then, people had made more careful calculations and said, okay, maybe it's somewhere in here. By 2008, that region had been basically excluded. And so you went to a one loop correction, and that gives you this sort of region. Already in 2008, I felt like we were very far down this path of looking for something and failing to see it. So I asked at a conference then, you know, how much of the probability is in this head and how much is in the tail? Because, you know, the tail will look a lot more probable if we lop off the head. And the answer was, oh, yes, yes, it's 98% of the probability is up here. We'll find it. Well, as I'm sure you're aware, that has not happened. And at this point, we have basically excluded all of the parameter space in which we could reasonably have expected WIMPs to live. You can still get away with it. You can lower the cross-section further. You can make the mass larger, so it is way off to the right of this plot and evades the limit that way. With some extra special hand-wringing, you can avoid it to the lower mass side, the so-called light dark matter. That does require some special pleating, and it's also a terrible name. It's lightweight, but it's certainly not luminous. So I could go on just about the dark matter for a long time, but that doesn't get us anywhere. I will talk about galaxies a bit, which is what I work on, and something that cosmologists seem to underappreciate is how precise things are in galaxy dynamics. I've really met an enormous number of people who simply say, well, galaxies are small, they're nonlinear, we don't care what they do. That's just not scientific, right? You have to do everything. An important fact is that galaxies are made of gas as well as stars. So this is an optical image of a nearby spiral galaxy. Here's the near infrared image, which is useful because that's sort of the closest you can get to a stellar mass map. That's what we need for the Poisson equation. And then there's a distribution of atomic gases traced by the 21 centimeter line. The scales are correct. The H1 goes out much further than the stars, at least to the eye. And that's fairly typical. From those 21 centimeter data, you not only measure the gas distribution, you also measure the rotation speed. And so that's what's plotted here for this galaxy. And of course, you notice the classic result that the outer part of the rotation curve is essentially flat. You can calculate using the Poisson equation and the observed distribution of stars and gas what the rotation curve ought to be if that's all there was to the story. And of course, there's this deficit that we call dark matter. But as Bekenstein pointed out, this is really a discrepancy that sets in at a particular acceleration scale. So I've been at a lot of physics colloquium where I'll see a picture like this. Okay, rotation curves are flat, therefore we need dark matter, and then the speaker is off talking about his favorite dark matter model. That is only a partially informed opinion. This is what we knew when we invented the WIMP paradigm. But there's a lot more to this story, and that should inform how we build theories going forward. And for the most part, it doesn't seem to. So as was kindly mentioned, I realized at some point that a critical correlation here is not just that rotation speeds become flat, but the amplitude of that velocity scales with the mass of the galaxy. Really massive galaxies rotate fast. Those that are low mass are very slow. And of course, people had already observed these before ever I came on the scene. And so I was relegated to doing these little dwarfs down here. And of course, this had been noticed before by Tully and Fisher with their famous relation. And that was just seen as an empirical correlation between the luminosity and the line width, both of which are just proxies for the underlying mass and flat rotation speed. Those are what turn out to be the really critical parameters. If you leave out the gas, as you must do if you're just using luminosity, then you find that these gas-dominated galaxies all fall down here. But if you include the gas, which is the majority of their mass, then they're on the same relation. So you have to include both. The other striking thing about this relation is that there is a characteristic acceleration scale, and that is that line. That's just in the data, the line, the data follow a line of constant acceleration. So no theory is necessary there. That's just a scaling that you can work out of the observed velocities and masses. Now, I have worked a lot on low surface brightness galaxies, and I had an important prediction for them, which declined to come true. So let me quantify what I mean a little by low surface brightness. Here are two galaxies as they appear on old sky survey material. Nice typical spiral galaxy at top. And at about the same distance on bottom, this little smudgy thing is one of my low surface brightness galaxies. So we can zoom in on that and, you see there's some, well, there's not much to see. So you, shoot, don't do that. Sorry. I hate it when you hit the wrong button and you skip way ahead. Where were we? Yes, sorry about that. Basically, you have to go to a bigger telescope and take a better image. And now I've turned up the gain on the better image. And you can see that the low surface brightness galaxy doesn't have, in fact, have spiral arms, albeit feeble ones. And the diameter of this object is comparable to that. And they were chosen for this illustration because they're about the same distance. So the size is the same. What's different is that the stars are more spread out, and that's what makes the low surface brightness galaxy low surface brightness. Now, at that time, and this is again the early mid-90s, we knew the Tully-Fisher relation, but we really only knew it for high surface brightness galaxies. Remember, Newton told us that B squared goes as GM over R. So if you look at low surface brightness galaxies, you're taking the same mass in stars and spreading it over a large radius. So their contribution to the velocity should go down, and you should see that as a residual in Tully-Fisher. That was my prediction based on Newton. It's really hard to avoid that. And so I've binned up the data by surface brightness, and that's what each of these lines are for lower and lower surface brightness. But you'll notice the points, the data did not get the memo. They're all rigorously right on top of the same Tully-Fisher relation, regardless of surface brightness. And the predicted effect was not subtle, right? It should be really obvious, and it's not. Now, I could spend a whole talk telling you about the ways in and out of trying to get around that. And the short answer is that the only way to do it is to fine tune the answer. Because it gets worse than that. Here are two galaxies that are essentially the same. One very low surface brightness galaxy, UGC 128. One very compact high surface brightness galaxy, NGC 2403. When you sum up all the stars and gas, they're basically the same mass. And they have the same flat rotation within the errors. So they're exactly on the same point on that Tully-Fisher relation. You can't tell them apart. But if you look at their rotation curve, you certainly can tell them apart. The low surface brightness galaxy, and you can see by these lines, this is the predicted rotation curve for the baryonic component. It's been stretched out, as I described, for the low surface brightness galaxy, and the total peak is less. They contribute less overall. And so you would think if they're sitting in the same dark matter halo, whatever your prior assumption is, that ought to drag down the velocity a little. And it doesn't at all at large radii. At small radii, you see exactly the difference that you would expect. A concentrated galaxy has a rotation curve that goes up fast. Low surface brightness one that has a rotation curve that goes up slow. So they know perfectly well about the distribution of baryons at small radii. And then by large radii, somehow it only remembers about the mass and not the large radius. These are the same rotation curves, normalized now to the scale length of the disk, which of course is much larger for the low surface brightness galaxy. So in physical units, you can tell the difference. Normalized to the length scale of the disk, you cannot. And so whatever is going on, the dynamics know about the distribution of light in considerable detail. It's not like you can just plop them in the same dark matter halo and say, oh, it's the same. That does not work. And this is generally true. So I've now plotted the rotation curves of all the galaxies in our spark sample as the centripetal acceleration required to give that rotation curve, so v squared over r. And I've binned it up by the surface brightness. So very low surface brightness galaxies are blue, very high surface brightness galaxies are red. And you can see there's almost a perfect spectrum, right? The surface density is strongly related to the dynamics that you get, just the surface density of the stars. So Okay. They put the in button right next to the forward arrow button on this keyboard, and that's obviously causing me difficulties. So let's try it again. We'll just skip that. So there's a way of quantifying that dependence on surface brightness that turns out to depend on acceleration, which is why I plotted acceleration there rather than the rotation curve. So here are the rotation curves for 3 galaxies: a really strongly bulge-dominated galaxy, one with a really pretty high surface brightness disk, and one with a low surface brightness disk that's more gas than it is stars. They have very different rotation curves, right? That's a traditional representation. There's the observed rotation. The blue line is the prediction from the distribution of baryons acquired by solving the Poisson equation for what you see in the stars and the gas. But, you know, we don't have to plot exactly that. We can plot that centripetal acceleration, so b squared over r, against the acceleration the baryons predict, essentially b squared over r for those blue lines. And then you can see that there is a deviation up at small radii, high accelerations. There isn't really a discrepancy. And as you go to larger radii, lower accelerations, the discrepancy kicks in. And that's important because as you look at the next galaxy, leave the first one on as the gray line there, it just continues the same trend. And so to this one, there's no region where the stars explain all of the velocity as they do in the first case. And yet it falls on the same trend line in the acceleration plane. And so that's the what we call the radial acceleration relation. These are now all the galaxies that we had available to us plotted together as a histogram and a grayscale, blue scale, whatever you want to call it. And you cannot distinguish individual galaxy rotation curves here. You know, if you squint and say, okay, well, there's a little hook there and a little wiggle there, those are not significant. As near as we can tell, everything just falls on this relation. And this was really, we knew about this already from optical data, but the scatter was much worse. When we got enough near infrared data to do this, everything just lined up much better than we really expected. And so that's an indication that what we expected was true from stellar populations, that the near infrared was a good tracer of the stellar mass, is actually true. We know that's not true for the optical part of the spectrum, and the variability goes away when you shift to near infrared. So just an empirical statement. There is this ubiquitous acceleration scale in the galaxy data, and we see it in 3 logically distinct ways. One is the Tully-Fisher relation, as I described. One is the bend in the central density relation, which I skipped. And finally, in this radial acceleration relation, which utilizes all of the rotation curve data. And within the errors, it's the same scale. That did not have to be true. So if nothing else, there is something special about this scale, which is where the dark matter problem appears, or as Bekenstein said, the acceleration discrepancy. So this is the amplitude of the discrepancy, basically the ratio of total mass to luminance mass that you need to explain the data, as a function of the predicted acceleration. And, you know, we understand gravity perfectly well over 20 orders of magnitude in acceleration up to, you know, the mergers of black holes that we observe with LIGO, down through where we live here on the surface of the Earth, all the orbits of the planet. There's Pioneer 10 with the famous discrepancy included. It's so small you cannot tell here, regardless of what its cause is. And then when you get down to this scale around 10 to the minus 10 meters per second, it's roughly 1 angstrom per second, then all of a sudden you need a lot of dark matter. So there is something special about that scale. Now, this came as a huge surprise to me. because you don't expect it in terms of dark matter. And I had predicted in terms of dark matter that there ought to be a shift in Tully-Fisher, and I was wrong. The only person who predicted that right in advance of the observation was Milgram with his theory MOND. So that's the other branch of the tree. So let's talk about that a little. And here the idea is that you modify the force law rather than invoke dark matter at an acceleration scale. This is not a length scale. Those are different things. You can basically exclude theories of gravity that modify the force on some scale larger than whatever, a kiloparsec or something. That clearly does not work. But there seems to be something to this one. And it's really weird. Theoretically, above this scale A0, everything is normal and Newtonian. Below this scale, really low accelerations that we only encounter in extragalactic astronomy. The acceleration goes over to this strange form where you calculate what you would have gotten from Newton and multiply it in quadrature by this new scale. And this only happens at low acceleration. So G bar here, the Newtonian prediction is less than that. And so the net effect of this is to basically magnify, amplify the Newtonian prediction. And so I was blissfully unaware of this. Sometimes I wish I had remained unaware of it, but at some point I realized that Milgram had actually made predictions for this. Right in his original 1983 series of papers introducing the theory, he says that disk galaxies with low surface brightness provide particularly strong tests. Well, here, because I was interested in low surface brightness galaxies, not because I knew anything about MOND, by the mid-90s, I had done exactly the right experiment to test this theory. And, you know, the attitude I had was, oh, finally I have the data to disprove this stupid theory. That was my attitude going in. And so he made this list of predictions that I've lummed off here. And one was that Tully-Fisher should have a slope of 4, a normalization that depended on the value of the acceleration constant. Really, it should be zeta over A0, but that's a geometric thing. That fundamentally is just a relation between what you see and what you get. The mass of normal matter there is what gives you the flat velocity. There's no dark matter involved. And what had caught my attention was that he explicitly predicted that there was be no dependence on surface brightness. This was exactly what I had been banging my head against the wall for months and months trying to understand and failing to do so. So that did impress me. But I still, you know, was like, well, okay, you got this one thing. Surely it's wrong. And there were these other predictions. So let's go ahead and see what he said. So one of the things he said in those early papers is that the dependence of what you computed for the conventional mass to light ratio would depend on radius and surface brightness. So here are the high surface brightness galaxies. As you go out in radius, the acceleration goes down, so the discrepancy goes up. As you go to lower surface brightness galaxies, you're already starting at lower surface densities. That means lower acceleration. So the discrepancy is bigger sooner, and that gets progressively stronger effect. So when you get to the lowest surface brightness galaxies, they need dark matter right down to the center. Yep. He explicitly said how the shapes of rotation curves varied, and this is important because at the time he built the theory to give you flat rotation curves. That was the motivating thing. So just that they're flat doesn't, you know, give you any test. But at the time, the systematic shapes of rotation curves is not known, and basically they were all these high surface brightness things, and they were basically all flat. But he said, well, look, as you go down in surface brightness, you're predicting lower and lower accelerations. And so the shape of the low surface brightness galaxy rotation curve should be very gradually rising and only slowly turn over, whereas the bright ones should go straight up and flatten out. And yeah, that's what we see. Implicit in this is that, and he defined a quantity for the dynamical surface density. That's essentially the central density relation that I didn't talk about earlier, that the mass surface density had better correlate with the surface brightness of the stars, because that's what the mass is of galaxies, and that's what happens with scatter. Now, these are the original data that I had in the 90s with B-band data, so most of that scatter is just due to the scatter and the mass to light ratio in the B band. And really all this idea is that some recalls this is a formula that maps what you predict, the blue lines here, to what you get, the red lines there. It's just a way for amplifying the Newtonian prediction in a way that works. And so you can make fits to rotation curves of galaxies, and the only variable that you have here is the mass to light ratio of the stars, because we measure the light. We need to know the mass for this calculation. And so the one unavoidable free parameter is the mass to light ratio of the stars. And so we're just flitting through this in some way that I did not plan, and now it's going AWOL. So I don't know how I managed to do that, but you have been lucky to be witness to some of the most Zoom problems I've had since we started doing this. Yay, lucky you. All right, well, so, you can look at all those fits individually, and of course there are some problematic cases. But if you looked at them all together in the residual diagram, then you see what you'd expect for a healthy theory, is that basically there's some scatter around the prediction, and that scatter depends on how good the data are. And you can see there's a big beard of data at small radii. These are the worst data where it's hardest to measure things accurately. It's exactly what you'd expect. Moreover, there is a test built into that. We have a pretty good idea of what mass to light ratio is reasonable for stars at this point. And so you can ask, okay, what mass to light ratio is required by these fits? So that's what's plotted here, one in the B band, here in the K band. And what's expected for the stars? Those are the lines. This is an old plot now. So the lines are from Bill and DeYoung, 2001. And the data points are just what you need to fit onto the data. And it's not just that there is some, it's about one, which is the, approximate number for the mass to light ratio. But there's also a slope that depends on the color. It's a stronger slope in the optical than in the near infrared. And there's also an amount of scatter that you expect to be bigger in the optical than in the near infrared. And the fits to the data are completely consistent with that. And in fact, it would be hard to imagine a more reasonable set of agreement with the data. So you do need to make these fits to the rotation curve with the one free parameter, and that one free parameter is completely consistent with the astrophysical check we have from stellar populations. So, what am I supposed to say? I went into this expecting that I would disprove this theory. And instead, everything that Milgram had predicted a priori came true. Just can't be right, can it? So since then, I've been, every chance I get, try to make a new test of this theory. There are details like the fits here. This you can explain with Newton. There's a little concentrated bulge, and so that predicts that little uptick. That has to be true in MOND. It can be true in dark matter, but doesn't have to be. Depends on the dark matter distribution. But this is also true. These features translate in low surface brightness things where the discrepancy is huge. And that really does not make sense in terms of dark matter. Here, the halo dominates, and so it should just smooth right over this little bump in the baryon distribution. Yet this is the sort of feature that we observe so frequently. It has a name, Sanchezi's law, or Rinzau's rule, because Rinzau-Sanchezi noticed that this was something that galaxies did a long time ago, just empirically. The only natural explanation for that is a force law like Mond. We can also use it to just do predictions. So I realized, if you just go blind, assume your best guess for the mass to light ratio, you can try to predict rotation curves and other things. And so this is what happens for that bright galaxy I showed you at the beginning. Basically just guessing what the mass to light ratio gives you an almost perfect description of the data. You miss the inner point. And that's because the guess for the bulge just undershoots it a little bit, which you expect, right? There's some scatter there. You can do the same thing in lambda CDM now if you adopt some prescription like abundance matching for predicting the halo mass based on the stellar mass. So here's the same stellar mass, same distribution of baryons. For this bright galaxy, the nominal prediction is that it should live in a much bigger halo than is allowed by the kinematic data. And so you say, well, that's the wrong abundance matching relation. Adopt a different one. Sure, you can do that, and you get a different wrong answer. You get another one, then you get a different wrong answer. And lambda CDM makes no unique prediction. You get things all over the map. And that's really what bugs me, is that the predictions of Mond are unique and they come true. Whereas lambda CDM is like, yeah, we can do that, we can do that, we can do that. That's not healthy for a theory. Another example, I said other things, were the dwarf satellites of Andromeda. A decade ago, the PANDAS survey was going on, and they were discovering new dwarf satellites to Andromeda all the time. So Andromeda is in here. This is a map all around it, around M33. Grayscale showing the density of red giant stars in that area. And all the circles highlight the locations of dwarfs, some of which were already known, and some of which they discovered new. And so I realized that's all the information that we need to make a prediction in Mond. How many stars are there? What's their distribution? And so I could make a prediction for the velocity dispersions of these objects as they were being discovered. And people were doing the follow-up work so fast that it was hard to predict and write up a paper before they told you what the answer was. But I did this as best I could. And what's shown here are the velocity dispersions for each dwarf. So that's Andromeda 1, Andromeda 2, 3, so forth. And so the points with numbers next to them, those are the actual observations. The circles are the predictions. And there's one problematic case, Andromeda 5. Predict about 6 kilometers a second, we observe something like 11 or 12. Every other case is consistent with Mond, except for those things that has 6 stars observed. Well, 8 stars observed, okay. Everything else is consistent with what Mond predicts. And in a lot of those cases, it was a true a priori prediction. The prediction came before the observation. And this is an especially good case is Andromeda 28 here, because it's clearly in the isolated regime. The prediction came first. There are some other good cases here, but that was the one I thought was best when I wrote the paper in 2013. Again, what am I supposed to say? That he's wrong? You can look at this and say, well, it gets this one case wrong, that falsifies the whole thing. Okay, maybe. You expect to mess up in astronomy once in a while, so it would be strange if that didn't happen. But it still doesn't explain why this formula works to predict all these other objects. That should not happen in terms of dark matter. One of the weird and kind of unique predictions of this strange theory of Milgram's is that there is this thing called the external field effect. If something's all by its lonesome, then that's the mass estimator in the low acceleration regime. A high acceleration regime, we don't even notice it. We build an experiment on the surface of the Earth, for example. It's still in the high acceleration regime, so again, you don't notice it. But if you're in the low acceleration regime and you're exposed to an external field, it's also in the low acceleration regime, then you get this modified mass estimator that looks like Newton, but with an effectively stronger value of Newton's constant. And so some of the dwarfs I was just talking about fall in this regime where their acceleration as they orbit around their host is as strong or stronger than the internal accelerations of their individual stars. And so I've identified some matched pairs of dwarfs that are basically identical in terms of their luminosity and scale lengths. But some are far enough from their hosts that they're effectively isolated, and others are in this regime where they're affected by the external field of the host. And you can see, if you match up these matched pairs, that the predicted velocity is higher when they're isolated, and so are the data. So Andromeda 28 again, you get up around 5 kilometers per second is the expectation. In close to Andromeda for Andromeda 17, otherwise the same galaxy, it's only a couple kilometers a second. You know, we see this effect. Unfortunately, the data are not good enough to say it's a 5 sigma effect, but this is unprecedented in dark matter. You just have to add another knob that makes it look like MOND. Can keep doing this. I did the same thing for Crater 2 when it was discovered in 2016. At this point, it was so old news to me that I the paper was discovered. I did the math and I tweeted the answer. That was the only prediction I made, was just on Twitter. And after a while thinking about it, it's like, well, yeah, it's an interesting case, so it's worth writing up. And it's interesting because it's tiny luminosity, right? It's a little globular cluster, but it's spread out over a kiloparsec. Crazy diffuse thing. And so if you look at lambda CDM, here's a discussion by Mike Boylan-Colkin, and he was talking in this paper about the too big to fail problem. Because there are no galaxies up here when there are dwarfs down here. But basically, no one contemplated a velocity dispersion, especially out at 1 kpc, as low as what MOND predicts. It should be up here somewhere. And all the scaling relations, not true predictions, but scaling relations, led us to expect, you know, okay, 10 to 17, somewhere in this ballpark. The MOND prediction was 2. Should be 2 kilometers a second. That's different from 17. And it was the MOND prediction that came out right. Again, this is a priori in complete ignorance of the data, just what the theory predicts. And I had to add a piece to their plot in order to even show this object down here. It's way out at large radii where the default halos all predict a lot of velocity. So I'm still left wondering, why does this happen if we live in a universe that's run by cold dark matter? Why does MOND get any predictions right? It shouldn't. And this is a puzzle that the community has, for the most part, failed to engage with. There is a recent detection from my collaborator at Busan in Korea, where there is a statistical detection of this external field effect in giant galaxies. So just as the dwarfs orbiting a massive host can be affected by its field, even a giant galaxy can be affected in its outskirts by the external field imposed by the external field from everything else in the universe. And when he said he wanted to do this experiment, I'm like, yeah, that's true, but we'll never be able to detect it. And in a lot of cases, we don't, right? These are negative numbers, they're unphysical. But statistically, the median detection is formally different from zero. So this is a formal detection of the external field effect on other galaxies. That's just unprecedented in terms of dark matter. You can't explain it with that. So, you know, I'm reminded of what Newton said, that for his inverse square law of gravity, he said everything happens as if the force between two bodies is the product of their mass and the inverse square distance between them. And that as if was really important. That's why I've added the emphasis there, because remember, Newton at the time was given a lot of grief for action at a distance. It seemed like magic to other scientists that somehow the sun could reach out and exert a force on the planets. You know, how was that force conveyed? And so he was at pains to say, look, I don't know how that works. It just happens as if. And so I think at this point, we can safely say that that is true for galaxies too, that everything happens in galaxies as if the effective force law was the one that was predicted by Milgram, the MOND. It doesn't have to be fundamentally a modification of gravity, but any viable theory has to explain this, and it has to do so naturally, not by adding a bunch of feedback and other knobs. That's just not going to work from the get-go. But it could be, I mean, the obvious interpretation is the predictions all come true because there's something to it. So I don't have time to talk about every other thing you can do to test it, of which this is still an incomplete list. I do want to mention clusters of galaxies, because that is, I think, the biggest problem. I'm running out of time, but I'll quickly go through this. There is a residual discrepancy in MOND. That here's the plot of the dynamical mass against the observed mass for a bunch of clusters of galaxies. This is just a Newtonian calculation. This is the calculation in MOND. And this appears all the way back in our review article 20 years ago. And the problem is that the MOND data do not fall on the line. Well, it's the same data. The MOND calculation does not suffice to move the mean down to the one-to-one line, as it should if MOND is the right force law and all the stuff we see is all the mass that's there. So that seems terrible for the theory because, you know, you're trying to get rid of dark matter, and here you need some dark matter. And I agree, that is terrible. On the other hand, over here, what's the prediction? Right, back in the days of Zwicky, we didn't know about the baryonic mass in gas. So all these points would have fallen way, way, way off to the left, lower observed mass, and the net discrepancy would be much larger, and we're fine with that. Basically, if there's no discrepancy, we say there's no dark matter. If there's some discrepancy, there's some dark matter. If there's a huge discrepancy, there's a lot of dark matter. There's no prediction there. So it's problematic to even compare the theories on the same footing. A famous example of this is, of course, the bullet cluster, which I won't go through in detail, but I'll just say that it's showing the same discrepancy that all those other clusters show. So it's not really surprising that it shows the same discrepancy, but it's still a problem that there's a discrepancy, right? But you know, people talk about clusters or they talk about galaxies. Here they are both on a large scale. That red dashed line is MOND's prediction. It misses up here. That orange line is basically what you expect for cold dark matter if you can see all the baryons associated with the halo. That's almost true for clusters of galaxies, but it's not remotely true for individual galaxies. So who's doing worse here? So both paradigms suffer a missing baryon problem. This is the problem in MOND. There's not enough baryons there to explain the dynamics, but that's also true in lambda CDM, just in different systems. So you know, you can decide for yourself which is worse. All right, I've talked long enough. So now that I know there is an end button, I will skip to that and tell this little story about my daughter and Tom Shutt's daughter. Tom Shutt was a colleague here at Case Western who works on dark matter detection experiments. He's since moved to Stanford, but he's been involved in some of these really large xenon experiments, and it's just amazing the technology that they have developed. The experimentalists have been phenomenally successful in not detecting something. They really should have. They've done their job, and it's the theorists who keep changing their story. But anyway, back in that 2008 conference I mentioned, it happened to be here on the same week that my daughter's birthday was. And my daughter Isabel's birthday, best friend at the time was quite independently Tom's daughter, Maddie. And so I came home after this working at the conference, and there were a bunch of kids in the house, and Maddie is of course there. And so I looked at her and said, "Oh, Maddie, I was just working with your dad." And she looked at me and said, "Oh, I thought you guys worked against each other." And ensued this following debate, which Tom became obsessed with recreating. So I'll let the girls tell it from there.
Dark matter does too exist. If dark matter didn't exist, then the eighth dimension would not fit into the quantum theory. No. We just corrected it. No. The eighth dimension is not defeated by the quantum theory of faith.
And that kind of tells you the story of the last quarter century of my career. So thank you for your attention. Stop sharing if I can figure
Thank you. Thank you very much. Thank you very much for your talk, Professor McGaugh.
Sure.
Very interesting. And it seems sometimes that in Twitter, it looks like the recreated fight between your daughter and
Yes.
and Mrs. Shutt.
That is the level of dialogue a lot of times.
Yeah. Yes. We have time for some questions from the audience. All of you are unmute or can unmute yourself.
So Miguel, you have
Miguel Pino.
You're muted.
Yes. Hi. Yeah. Hello. Can you hear me? Yeah. Thank you.
Yes, I can hear you.
For some reason, I cannot start my video. I don't know why, but it doesn't matter. Well, thank you very much for your talk. You show a lot of evidence, and for some reason, a lot of people feel uncomfortable with MOND. So I don't know. It seems more like well, something similar to what the girls were fighting about. Huh? No, I have two very naive questions actually. The first one is that you mentioned that there's a typical scale in MOND theory, which is an acceleration scale, and it's very low. It's a very low acceleration. So my question is whether that allows to be measured in a more controlled situation, like a laboratory or something like that. And my other question is, as Newtonian gravity is like a low energy regime of general relativity, is there an analog for MOND, like a high energy theory that might from which MOND might arise?
So that's a second one. Well, they're both good questions. The second one is very open-ended. So let me address the first one first. Basically, you would like to do an experiment that tests this idea. And unfortunately, the external field effect makes that very hard, because you can build an apparatus in a lab on Earth that has very precise measurements of interparticle accelerations that are tiny and are done in the low acceleration regime. And there are IED-VOSH type experiments that have achieved that level of precision. But the entire apparatus is sitting on the surface of the Earth. So the prediction is not the Mondian interaction one, and this is one of the many things that makes the theorist's head explode. It's a non-local theory, so the fact that it's sitting in this 1G acceleration field basically blocks out this, screens out, if you like, this minor acceleration effect. You can imagine being able to detect it, but it depends on how you transition from the low acceleration regime to the Newtonian regime. If that's very, very slow and gradual, you might detect some tiny residual. If it's quick, then you have no chance. So what you'd really like to do is build this apparatus and send it to some extremely low acceleration part of space. To get into the Mond regime, you have to get away from the sun by about 7,000 AUs, about 1/10 of a light year. So you have to be very patient if you want to send an experiment out there. And even then, the part of the galaxy we live in is not really in the low acceleration regime. It's close, but it's slightly above A0. So even there, you're in this sort of external field effect regime. Now, a precision physics experiment at that distance, I would think, should still be able to detect something. But you got to get there. That's the hard part. I have heard one proposal to test this on the surface of the Earth. It is specific to modified inertia. So I didn't even go into this. It could be a modification of gravity, the GMM over R squared, or it could be a modification of F equals ma. You could go either route there. That seems even crazier, right? But if that's the case, then there is a claim, and I have not tried to check this, but if you add up all the vector accelerations as the Earth spins and goes around the sun and the sun goes around the galaxy, et cetera, that there is a moment at spring equinox where there is a patch of Mondian effect that sweeps across at a latitude of Greenland. So you could imagine building your precise thing and putting it at the right place at the right time and seeing that transient effect. It sounds crazy, right? I don't know. As far as your second question, can this come out of some deeper theory? I hope so. I don't know of any. I know a lot of theories that don't do this. I don't know that people working on quantum gravity have paid a lot of attention to this, which is part of the problem. I mean, I feel like they're not making any progress because they're playing with they're playing solitary without a full deck of cards because they don't know about this or don't take it seriously. That's not true of all of them. Lee Smolin has tried his hand at this. And I have heard arguments about whether you're in the infrared or ultraviolet limit, to put it in those terms, but I haven't seen anything really promising come out of that. The most promising theory at the moment is relativistic Mond, R-Mond or REL-Mond, by Skordas and Zlosnik. And that was just published this year, and they were able to show that they can fit both the cosmic microwave background power spectrum and the galaxy power spectrum, which is something I didn't feel I had time to talk about, but that, like clusters of galaxies, has been something that has eluded us for a very long time. So that is at least a step in the right direction. Whether it's the right theory or not is a bigger question.
Okay, thank you very much.
Another question? With respect to this relativistic Mond, I was impressed because it seems they succeed in showing or fitting, I don't know how to say it, the third peak in the CMB.
Yep.
And this for me was very impressive.
Yeah, this is something I've struggled with for a long time. So let me share my screen again, because I did have this very plot handy. That it's not to have worked. No, I have to. Okay, so this is the prediction I made over 20 years ago now, that line. And it did get the second peak right. So, right, that was what I was trying to predict at the time. So, yay, that worked. The equivalent lambda CDM prediction at the time was higher. And the fix was to increase the baryon density to increase the damping. So everybody says how great deuterium agrees with the CMB, and that's true now. It was not true ahead of time. Deuterium has changed, and it's changed in the right way. But what the same model predicts a low third peak, and instead you observe this high peak. So for a long time, and still to me, that's really the best evidence for cold dark matter. And it's just been an intractable problem because you need the relativistic theory. And so that's what Skordas and Zlochnik have provided. And the plots on the bottom are the plots from their paper. 2020, I guess, is when it appeared on AstroPH, but on the archive, but it's in PRL now. And in fact, the first version, they didn't even show the power spectrum because always people want more. So just fitting the third peak as they do here was an amazing thing to me. And the refereeing process was apparently long because I'd seen this at a conference a couple of years ago before the pandemic. You know, the obvious thing was, well, what about the galaxy power spectrum, the plot on the right? And they said, yes, we can do that. Well, now they've shown they do it, or at least how well they do it. To me, that means these things are possible. Doesn't mean it's right, but it was an important advance to show that you could get this at all. Really, the argument that people have, and now it's just an excuse, right? The argument people have given for not considering MOND is that it cannot possibly explain the third peak in the microwave background.
Yeah.
Oh, that's not a valid argument anymore.
Yeah. We have time for another question.
I don't buy mostly.
Okay, it seems there are no more questions. Well, Miguel did the question about the origin of this acceleration scale. I think that is the more important question that remains to be answered in this scheme.
Yeah. So who ordered this, right?
Yeah.
Where does it come from? And it does seem like if it's real, then it may be really a new scale of nature, like Planck's constant or Newton's constant. And if so, you really feel there needs to be some fundamental principle behind it. And that's lacking in any theory that I've seen so far.
Yeah. Okay. Thank you very much, Professor McGaugh.
My pleasure.
I thank also the audience, and you are all invited for next week in our seminars. Thank you very much, and we see each other. Bye.
All right. Take care. Thank you.
Thank you. Bye bye.
Bye bye.